video, I'm going to explain a Java program that simulates interactions among animals on a 2D board. This is a program that illustrates the usefulness of Java inheritance and also polymorphism and dynamic binding. And it's just helps students who want to learn these concepts understand them better and find out why Java polymorphism is useful and basically see an example of it on a real world setting. So what I'm going to do here is I'm going to explain this program completely. This is the completed program, but you can extend this by adding more classes to it, which I'm going to explain in a minute. Let's first understand what the simulator is going to do. The simulator is on a 2D board, which is an n by n square shaped field, where n is given by user through keyboard. And then there are two classes of animals on the board. One is prey, one is predator. This current version of the program has only one type of prey, which is a mouse, and then two types of predators, which are cat and alligators. And then basically in each step of the simulation, prey randomly moves to one of its neighboring squares. We don't have only one prey, we have k preys where the value k is given by the program. In other words, I should say for every type of animal we have k instances, which I'll show you in the program. And then the prey randomly moves to one of its neighboring squares in one of these 4 dimensions. Either it moves up, down, left, or right. Predator also moves to one of the 4 directions, but not randomly. The predator moves toward the closest prey, and neither prey nor predator can move more than 1 hop or 1 square in every step of the simulation. So if there's an animal on the board and it wants to move 2 steps or 2 squares to the left, it has to do it in 2 consecutive steps. It cannot do it in 1 step. And if a prey and predator happen to be on the same square, then the predator eats prey and prey will be eliminated from the board. If 2 predators happen to be on the same square, then the predator with higher power level eats the other one. And then if there are 2 preys or 2 predators with the same power level on the same square, then the animal with higher ID number is going to be moved to a random empty square. So it's going to jump to a random square in order to resolve collision on the field, on the square where both animals reside. So I'm going to illustrate all of that, and I'm going to show you where I implemented each part of this explanation in the program as I move forward, and I show you different classes. I'll explain like this is the code where I resolve the collision, or this is the code where I make sure one animal eats the other, or this is the code where the prey moves randomly. So I'm going to explain each single one of these statements inside the code of the program. All right. So I already have created 2 packages. One is called simulator, as you see on the left side, and one is called animals. The simulator is made of 3 classes, and the animals is made of 6 classes. So let's review the classes on the simulator first. We have animal simulation, which is basically the class that contains the main method. This is the main method, and Basically, it um, specifies the logical flow of the program and how the program is executed. At the beginning of the main, we are asking user to enter some integer for the board size. As I said, it's going to be a square-shaped board or field. N is going to be given by their user. It should not be less than 6 or greater than 25. If that happens, then we're going to end the program prematurely. And also, we're going to ask for the number of animals per type. And then the user enters another integer. That integer cannot be less than 2 or greater than 5. Basically, what I mean by number of animals per type is how many mouse in this case we're gonna have, because we had like one prey called mouse, or how many cats we're gonna have, or how many alligators we're gonna have. So if, for example, k is equal to 4, that means we have 4 mice, 4 cats, and 4 alligators, a total of 12 animals when the simulation begins, right? Also, uh, as you see here in this main method, I'm initializing the board using the values n and k. That method is basically is implemented in another class called board, which is going to get an integer and an integer n and another integer k, and it's going to create a new board for me and fill that board with multiple animals. In this case, as you see, with k cats and k alligators and k mice, and then it's going to return it at the end. What is board? Board is the constructor of the board class, which basically um, initializes a two-dimensional array of squares with the dimension size and size, where size was the value that the user enters. We call that n, which is the number of um, rows and columns of the simulation field. And then I have an empty array list of animals, an empty array list of eaten. I'll talk about these later. Basically, this keeps track of all the animals in the simulation, and eaten would be empty after every step of the simulation. But in the middle of the step, in the middle of the simulation steps, the eaten array list can have more can have like members in it, and that basically means these are the animals that have been eaten in the current simulation step. At the end of the simulation, we're going to remove them from the list of all animals, and we're going to remove them from the grid so that they will be eliminated from further interactions in the simulation. So we'll see the details later, but I just wanted to tell you what the constructor does. And all of these are going to be instance fields. All of them are private instance fields that we are initializing in the board constructor. And then in this for loop, we are just initializing every single square of this grid, which was in size by size square shape field uh, by calling this new square constructor. The square is another class in the same package, which is basically representing one cell of the whole board. And that square class has a private field called animal with the type animal, which I'll show you later. This is basically the current resident of the square. If the square is empty, then animal is null. So if null, then that means the square is empty. And also I have a is empty method that checks whether the animal is empty. I have a set animal that sets the animal to animal, remove animal, which sets the animal to null, get animal, which returns the animal, and then get symbol, which is gonna either returns an empty character, or it returns the symbol of the animal. Later, I'll show you every animal has a symbol that basically allows us to print the whole board after every simulation. And basically, this way we can show the user how the simulation is proceeding, and how it just show the progress of the simulation to the user. Anyways, so I just showed you how the initialize board looks like. That was the first step of the simulation. We created a new board, and then we have these two big for loops to place animals on the board. The first for loop places all the predators on the board, and then the second one places all the preys on the board. So this is for predators. Now you might say, why did you put predators before preys? Uh, I'll show you later. Basically, the simulation happens in the following way. First, um, we move the predators, and then we move the prey. So this way, if the predator wants to eat the prey, they have an easy time eating them. So that's going to be a unfair simulation field, which favors the predator, not the prey. That's like how I did it. You can do it the opposite. If you move this for loop before the for loop of predators, then you first place the preys in the array list of animals, and that's gonna basically result in preys moving before predators in every step of the simulation. It's not a big deal. It's just one way or the other. Like I decided to do predators before preys, and then in this for loop, I have two while loops. The first while true picks a random number. You'll see a lot of random static instances that we use to get a new integer. In this version of the simulator, I decided to make random a public static instance, a public static field of the animal simulation. And I initialized it this way. I said this is equal to new random. If you want your output to be non-randomized and always get the same output, you can replace this constructor of random class with random zero. The zero is the seed. If you do this, then every time you run the program with a certain n and k, the output would be exactly the same. But if you don't put a number here for seed, every time you run the program, you get a different output, because the random number generator generates a random locations for the animals, and you will see a different simulation with different position of animals on the board, and the result will be different. But a lot of times when you're testing your program, you hate to see like a different output every single time, especially if your program is bogus and you want to find the bug of your program, you want to debug your program. So in those situations, it is much more convenient if you have random zero instead of random, because that's going to always show you the same exact field and the same exact movement of animals until the end of the simulation. But I'm just going to leave it as random for now. We're going to get back to it and I'll show you an example of how I run it with or without that seed zero. So I was talking about, placing predators in random locations. First, we get two random numbers, x and y, and these are randomly generated. As you see, random.nextInt n is going to generate a random number from 0 to n-1. It's uniformly distributed. Uniformly distributed means the chance of getting a number from 0 all the way to n-1 would be equally likely. That means the chance of getting 0 is the same as the chance of getting 1, is the same as the chance of getting 2, all the way to n minus 1. The same story happens for y. What are x and y values? These are the basically the coordinates of an animal that we're going to place on the board. So basically, we need to find out a random coordinates, like a random x and y coordinates for the new animal, and then place it on the board. That's going to randomly places animals on the board. It's going to kind of distributes them randomly around the board. And if the board is empty at that location at x and y, I showed you the is empty uh, method of the board. Probably didn't show you. I showed you the is empty of square, but that's very similar. If you want to check whether an x and y coordinates are empty, you just pass the x and y to the indices of your grid, which is a 2D array of squares, and then this is going to give you a singular square. Then you call the is empty. If this is true, then you return true. If it's false, you return false. And if you remember, the is empty method of the square was comparing the animal resident with null. If the resident is null, then it's null. Then it's empty. If it's not null, then it's not empty. So everything works beautifully so far. The is empty basically checks whether a certain coordinate x and y is empty. If it's not empty, that means we have previously placed an animal there and we have selected it again, because this random number generator may select one square multiple times. So you need to always check whether it's empty or not. If it's not empty, then we're gonna try again, because this while true keeps iterating as many times as you want. But if it's empty, then we're gonna place the animal. This time, this line basically places a new cat on the location x and y with this ID. The cat is a class in a different package that I haven't discussed yet, but we're gonna see it later. It's gonna basically initializes the ID, the location x and y of the cat. The cat extends predator, and predator is a child of the class animal, and animal is basically the class that is the superclass of all the animals that we have. All the preys and predators will extend animal. And we will get to that later. Let me finish the initialized board first. So we were talking about the method initialize board and how to add a cat here. As you see, by plussing ID here, we are making sure that every animal gets a unique ID. The IDs start from 0 and it goes up. So the first animal that you place has an ID 0, then ID 1, then ID 2, then 3, 4, all the way to whatever the total number of animals are. And then after this while loop ends, right here, after you break, after adding an animal on the board, you're going to break. The add animal also is another method you can take a look at. It's going to add the animal to the list of all animals. I showed you this was an array list. And then we are going to say the grid at index animal.get x, animal.get y. This is basically the x and y location of the animal. Dot set animal. That basically stores the animal on the square at index animal.get x and animal.get y. Get x and get y are basically getters for x and y, which is the position of the animal. And set animal is a setter for the animal instance field of the class square, which I showed you earlier. If you remember, this was the one. So that's how the add animal looks like. This is all inside the board class. All right, so I called the board classes instance method called add animal to add this animal to the board. And my animal is a predator, which is a cat, right? And I'll show you the cat class and other animals later. In this next while loop, I do the same exact thing, but instead of adding an animal, adding a cat, I will add an alligator, which is another kind of predator. And then in this for loop, I do a similar job as I did for the alligators and cats, but this time I only add the preys. So this is gonna add prey on the boards. And the X and Y are randomly chosen. That means we're gonna randomly choose a location. As long as that location is empty, we are free to place a mouse there, or if you have more praise, you just add them in the same place. And that's it pretty much. At the end, we're gonna return the board. Now that you have initialized the board successfully, it's time to go ahead and do the rest of the simulation. This is how the rest of the simulation looks like in the main method. We're gonna create a time instance, time variable that's an integer initialized to 0. That's gonna tell us which step of the simulation we are. At the beginning, time is 0, but after the first step time becomes 1, the second step time becomes 2, 3, all the way. We first print out the current time. We say this is the current time, and then we're going to increase the time by 1 because we're going to move to the next step. We are going to display the board after every single step. The board display is a method which I'm going to show you right now. It's in the board class. It starts by printing a bunch of dashes that's going to represent the straight line. And at the end, it's going to print the same line that's going to basically separates this current display of the simulation from the future and previous displays. And it's going to make the console look nicer and easier to read because you have like separating lines. And then in this nested for loops, what I will do is I go over every row and column of my grid and basically print every grid ij symbol followed by a vertical line and a tab. The vertical line is like the borders of the tables, the vertical borders of the tables, and then the tab is going to make sure that we have alignment over cells of the same column. And basically I, which is X in the class animal, and when you want to specify the coordinates, we use X and Y. So I is basically the X and J is the Y. I shows the row number and J shows the column number. So when we say X, that means that means which row we're talking about. Y is the columns, right? So when we say X is 4, that means we are talking about the row number 5, because the first one is number 1 with I equal to 0, then I equal to 1 is number 2, I equal to 2 is number 3, I equal to 3 is number 4, and I equal to 4 is number 5. So when I is equal to 4 or X is equal to 4, that means we are on row 5. And then columns start from 0. When J is 0, that means we're in column 1. J is 1 means we have the second column. J2 means third column. J3 means fourth column. J4 means fifth column, so on and so forth. So basically, the top left corner would be 0, 0. And the bottom right corner would be n-1, n-1. That's the whole coordinate system. Let me, just to make sure everyone understand how it looks like, I'm just going to draw the things here. Let me use a different color. The blue is not a good color here. So let's say when I go down, this is my X coordinate and this is the Y coordinate. It's kind of the opposite of what we're used to. And when we say, for example, 4 and 3, we mean here, right? This is 0, 0, and this is going to be, let's say n is 7. So this is going to be 6, and this is going to be 6, and this is the bottom right corner, right? And then we are going to print the animals in the same order. We're going to print the first row, then the second row, then the third row, then the fourth row, then the fifth row, then the sixth row, and then the last row, which is the seventh row. So we print them in that order. And after every row, we are going to print a new line here to make sure that we go to the next line and print the next row and column. So that's how things look like. That's my display method. And now let's go back to the main method and let's see the rest of it. We have this for loop as long as the simulated.Step method doesn't return false and the time is less than or equal to 50, we are going to print the current time and we are going to display the board again. This simulated.Step is going to make sure that the simulation is executed for the next step. It's going to move all the animals for one step, and if one animal eats the other, it's going to eliminate the eaten one. And then basically, we are going to display the board and then increase the time for the next round. After this for loop ends, either because all the preys are gone and the simulation.Step returns false, or the simulation has taken so long that we have reached to the time 50. That's pretty much impossible to happen. But in some weird scenarios, if this happens and time becomes 50, then basically we're gonna stop. We don't want to continue simulating, but that's almost impossible. The main reason of simulation stops is because the simulation.Step returns false. And I'll tell you when it happens. We are going to print a simulation and we're going to close the scanner that was responsible for getting the values of N and K from user through keyboard. All right, so last thing I'm going to mention before we go to the animals class is the simulated.Step, which is pretty complex. I mean, at least it doesn't look complex, but after I show you the move method of animal, you see it's pretty complex. In this simulated.Step method, I'm going to have a for loop over all the animals in my simulation. Originally, if let's say K is 5, we have 5 cats, 5 mice, and 5 alligators. That means we have like 15 animals. And this for loop will happen 15 iterations. If an animal is not in the eaten list, that means if that animal is not eaten by another animal in the current simulation, then we are allowed to move it because it's alive, we can move, right? So we're gonna call the move method on the animal that move this, and this is basically the board, and that's how you basically pass the board to the move method. The move method is defined in the animal class. Right now it's empty because this is the super type, this is the animal class, but all the children of the animal class, which are prey and predator, will override this method. But right now, we don't put anything because this is the generalized version of it, and we cannot generalize the move of every animal. If it was allowed to use the word abstract for this assignment, I would make this an abstract method. But because this is posted before you learn about abstract methods and abstract classes, I avoided using abstract. All right, so okay, so basically we're gonna call the animal the move on this board, and if it returns false, that means your move wasn't successful, and that's only because there is no prey on the board anymore, and then the predators cannot move around because they have no target to move toward to. So we are going to return false, and return false will terminate the simulation, as I showed you earlier. In the for loop, we say if the simulated.Step returns false, we're going to end the for loop, and that would end the whole simulation. And then you have a for loop over all the eaten animals, and we are going to make sure that those eaten animals are removed from the list of all live animals. And then we are going to clear the eaten after that. so that you don't keep Ethan occupied with the already dead animals. So they are removed, and then we go to the next iteration. And here we're gonna return true. That means the simulation step was successfully executed. Now I'm gonna move to the other package animal. I'm gonna start with the animal class, which is the super type of all other types. It has an X and a Y. X is the row index, as I mentioned, and Y is the column index. Fix it, mistake. And X increases as we go down, and Y increases as we go to the right. So it's kind of the opposite. And then our origin 0, 0 is on the top left corner of the board. That is correct. And yeah, that's pretty much it. There's an ID that is protected. X and Y is also protected because we're going to assume that all of these three instance fields are going to be accessible not only in animal, but in prey, predator, cat, mouse, alligator. All the subclasses of animal will have access to it. That's why we use protected, not private. And then I have a constructor for animal, which initializes all the three instance fields with the given values. Also, we have a get symbol, which returns X. This is not a real symbol. This is just a placeholder for the get symbol method. Later, all the animals are going to override this method. If it was possible for me to make this an abstract method, I would do that. This is a great candidate to be abstract because the body or the definition of this method doesn't really make sense here because the animal is unknown, so we use X as a symbol. But later, for example, for alligator we use A, or for cat we use C, or for mouse we use M. Then you have a move method. Again, it doesn't do anything. It returns true because all the subclasses will override this. Get ID will return the ID. You have a getter for ID, you have a getter for X, you have a getter for Y. These are all public getters for the protected instance fields that we have defined for this class. Also, you have a set position that sets the position of the animal to a given X and Y. That's like a setter for both X and Y. That's how I designed it. Then you have the prey and the predator both extend animal. This is a good time that I show you the UML diagram of this whole animal class. So if the animal is the super type of all types, all the animals types, we put it on the top, and then we say, this is the generalized type of two subtypes. One is called prey, and one is called predator. And then for the prey, I have another subtype, which is mouse here. And the predators would be, one is cat, and the other one is alligator. So right now we're talking about the predator on the right. It has a protected integer power level that's basically shows how powerful the predator is. The predators with a higher power level will eat the predators with the lower power levels. The constructor initializes not only ID, X, and Y, which are the identification number and positions of the animal, but also the power level. So the first three instance fields the first three parameters are going to be passed to the super classes constructor, the constructor of class animal. And then the other instance field power is going to be initialized directly using this assignment. Then you have a getter for the power. You have a move method, which is pretty interesting. The move method is going to move the predator toward the prey. So you need to first find the closest prey. I'll show you how this works. You need to call this method of the board class, which I'll go over it after this method explanation. If the closest prey is not null. If it's null, that means there is no prey left. But if it is not null, that means there is one prey at least, and that is the closest to the animal, to the current predator that we're talking about. You need to find out the closest prey's X and closest prey Y value. These are the locations of the prey, the closest prey, and find out the difference between the X's of this predator and the closest prey, and find out the difference between the Y values of this predator and the closest prey. Call them dx and dy, which are basically the delta x, delta y values. And then the new x and new y that we are going to move the predator to would be calculated based on the following logic. We first initialize those to the current x and y, which is the current location. Then we look at the sign of dx and dy. If the sign of dx is positive, that means the prey is further down, because as I told you, x means which row we are in. So if the closest prey x value is greater than the predator's x value, that means the prey is further down on the board. So it's we need to set new x to the previous x plus 1. So that's why we do new x plus plus. It was set to x before, now we need to increase it by 1. If dx is negative, that means the prey has a lower x than the predator, right? That means the prey is up or is in the higher rows of this field. That's why we need to do new x minus minus. And then if the x is 0, that means if it's neither greater nor less, that means both prey and predator are on the same row. Then you need to look at the columns. You need to look at the y. If dy is positive, that means the closest prey is in the right side of predator. So you need to set the new y to the previous y plus 1. So you need to do new y plus plus. And if the dy is negative, that means the prey is on the left side of the predator. That's why you need to subtract the new y by 1. That means the new y would be the old y minus 1. And then you need to call this update position to update the board with a new x and a new y. Now I'm going to explain the two methods that are called here. One is board.findClosest prey. This is basically finds the closest distance between the prey, between the location x, y and the closest prey. And then it returns the closest prey as the return value. So in order to find this out, you need to have a placeholder called closest prey, set it to null. At the end, we're going to return that. And define an integer that's the closest distance, set it to maximum possible integer. And then go through all the animals. If the animal is a prey, then check its distance from the location x and y. How do you find the distance between a given prey and a location x and y? you need to find the difference between their x values. So you just use math.absolute value animal x, get x minus x, and find the distance of their y values and get their absolute value. So math.abs of animal that get y minus y, and then you add these together. That's going to give you the Manhattan distance between the two. So if I want to show you a quick example, that would be something like this. Imagine you have uh, x and y here. That's the input of this method, find closest prey. And there is a prey here, right? Let's say there's a mouse here. The location of this mouse is x0, comma y0, right? If I want to find out the distance between the two, I cannot use the straight line distance. That's called the Euclidean distance. That's not possible because the animals are not supposed to move diagonally. They have to either move horizontally or vertically. That's why you need to find the distance that can be obtained by, these two horizontal and vertical lines. So you need to create a triangle and then find out this edge and this edge of the triangle. This is going to be delta x and y. So you need to find delta y here and then delta x here, and then just add them all together. But the delta x and delta y, one of them can be negative. So you need to find the absolute value of them. And then you need to add them together. This is called Manhattan distance between 2 points. So that's exactly what this line does. And that's why I didn't use, let's say, the Euclidean distance formula, which is based on the Pythagorean theorem. But, I just used the Manhattan distance. That's called Manhattan distance, like the Manhattan neighborhood in New York. That's what it's called. You find the distance. If the distance is less than the closest distance, which is going to be definitely true at the beginning because the closest distance is set to maximum possible integer. So at the very beginning, that would be always true. And then if that's the case, then we're going to set the closest distance to distance, and then closest prey would be the animal cast to prey. Remember, if you have a super type animal and then the subtype is prey, you can always cast the super type to subtype by explicitly mentioning it in parentheses, just like line 101 in this code. And then at the end of this for loop, after you finding the closest prey, you're going to return it. That's one method I wanted to show you. The other method that we used in the Predator's move method is called update position. And this is just to update the position of a given animal. This is the most complicated method of the whole Java program because it's going to handle all the collisions and stuff. So imagine you want to update the position of a certain animal. In this case, if you remember in the Predator, I passed this to it because this animal that I'm going to move would be my subject. That's the animal that we're going to move it, right, on the board. So we're going to move this animal to this location, to the new X and new Y. How do you do that? I'm going to show you the easiest case where there's no collision. So you need to get the animal's X and Y coordinates and use the grid indices to get the square with the coordinate X and Y. So that's the square that currently hosts the animal. Then you need to remove that animal from that square of the grid because we're going to update the position, so we're going to get rid of it. Then you need to find out which animal is in the new X and new Y. So if there's an animal there, we have a collision. If it's empty, then there's no collision. So grid new x new y that get animal gives you the current resident of the new xy square. If the new xy square is an animal, so if the current is an animal that is not null, then you have collision. But if it is null, there's no collision because the new square that you're going to move to is empty. In that situation, we have a very easy time updating the position. We simply say grid new x new y, the new square that we're going to move to, that set animal animal. That means move this animal to that square, and animal that set position new x new y. So the animal's new position would be the new x new y, because the animals always keep track of their location. So we're just going to update their current x and y. And that's going to pretty much end the update position method when there is no collision. But if there is collision, then we will have 4 very long if else statements. The first one is when both current and the animal that we want to move to, we're going to move them, are prey. So when I say current, that means the current resident of the new x new y. Animal is the animal that I'm going to move to the new x new y. So the animal wants to move to a location where the current animal reside. If they both prey, what's going to happen? By the way, the instance of is a reserve word in Java that allows you to find out whether or not a given object is an instance of a given class or given type. So when you do this, that means if the current is prey and the animal is prey. This is the logical end. If that happens, what's the collision rule? How do you resolve this collision? We say, let's find out which of these two animals, the current or the animal, which of them have the higher ID. The one with the higher ID should move to a random position. Then we're going to call this method, which is going to move the current to a random position. And then we are going to place the animal into location X and Y. And not only we are going to set the grid new X new Y set animal to animal, but also we are going to go to the animal set position method and pass these new X and new Y to it. So we're just going to update the location of animal to new X, new Y. Otherwise, if animal's ID is greater than current.id, then we're gonna leave the current animal to stay in that new X, new Y position. And instead, we are gonna move the animal to a random position. So current stays, animal moves. And this move to random position is pretty simple. In an older version of this code, which I have posted on Canvas before, this would get like 3 input parameters, but now I only pass 1 because I didn't need the other 2. After thinking about it a few times, I realized that you don't need to pass the other 2 instance fields, or the other 2 input parameters for this method. So keep this version. This is a simpler version. This private method basically moves an animal to a random position that is empty. So in this while loop, you need to first use the animal simulation.random, which is a random number generator, dot next int method to randomly generate 2 numbers, an x and a y. If the xy is empty, if the square at the index x and y are empty, then you're going to place the animal on that location, set the animal position to x and y, and then you can print a statement saying that the animal has jumped to this location because of collision, right? Some collision happened and one animal jumped to a location. And then you're gonna break out of this while loop. If not, you're gonna keep trying and trying until you find an empty location for the animal to move to. Let me go back to the predator class and finish this method. So basically, this method is going to call the find closest prey from the board class and update position from the board class. And then update position is going to take care of all the collisions. I only talked about the first collision, but you can guess what's going to happen for the other cases. For example, if you have two predators, if both current and animal are predators, and neither the current nor animal have a higher power level. If they have the same power level, then we are going to move the one with higher ID to a random position, just like when you had two preys. But if they're both predators and one of them, let's say the current resident, have a higher power level than the other animal, then we are going to print a message saying that the current animal ate the other one, add the other animal to the eaten list, and that's it. The current resident stays and eats the other animal. But in the case where the current animal has a lower power than the one that is going to come to this square, then you have to do the opposite. You have to say the animal ate the current, and you have to add the current to the eaten list, and you need to update the resident of grade new x new y to animal, and then say animal the set position new x new y. That's going to basically replaces the current with animal, with the other animal that has recently come to this new x new y square. In case where you have in the other cases where both animals are not predators and both of them are not preys, then one of them is prey, one of them is predator. In this case that you see here, current resident is a predator, and the animal that has just moved to this location is a prey. So what's going to happen? The predator is going to eat the prey, and we're going to add the prey to the list of eatens. Otherwise, we have the opposite situation. That means the current resident is a prey, the new animal that has just come to this square is a predator. So what's going to happen? We say the predator eats the prey. And we're going to add prey to the eaten list. We're going to update the animal in the grid new x new y, and then we are going to set the position of the animal, the predator, to new x and new y. And that's how we take care of the last case of collision. Okay, so that's all the collision rules that I am implemented it. Finally, the predator is done, right? I showed you all the methods in the predator. Now let's look at the two animals that extend predator. One is called alligator. Alligator gets an ID and an X and a Y. It calls the super classes constructor, which is the predator's constructor with ID XY, and the power level is 9. Because alligator is a powerful predator that can eat like weaker predators like cat. And then the symbol is A, and then we are overriding the symbol, which is A, and the toString method, which is very useful for those messages that says which animal eats which animal, will return the following message. Alligator with this ID at this location, get X, get Y. That's the toString method for alligator. The other predator, which is cat, has only the power 2 and the symbol C, and the toString method basically says this cat with this ID at this location. A string.dot format is the best way to create your own toString method. It's very easy to use it. The string.dot format gets the same kind of parameters that system.out.printf gets. So the first thing that you pass is a string with a bunch of placeholders like %d, %s, %c. %d means number, integer. %c means character. %s means a string. %f means float or double. %.2f means a double with 2 digits of precision, so on and so forth. And then for every percent placeholder, you just need to pass another parameter. And those values will replace the percent signs. And at the end, the string.dot format returns the string with this format. Instead of printing them like system.out.printf, it's going to return it like a string. The prey class, which extends animal, has a constructor similar to the animal, which just calls the superclass constructor, so it calls the animals constructor with ID X and Y, and it has nothing else. It doesn't have any power level or something that we have seen before. And then it has a move method, which moves the prey randomly. Unlike Predator, it's much simpler. You don't need to find the closest prey or anything. You just get the list of neighboring squares around X and Y. Get neighboring square is a method in Board class. Let me show you. It creates a list of arrays of integers called neighbors. Initialize it to a new array list. And then it considers all the 4 directions. This is the direction of Y plus, which we call it the right direction. This is the direction of X plus, which we call it the down direction. This is the direction of Y minus, which we call it the left direction. And this is the direction of X minus, which we call it the up direction. So we have up, down, left, right directions. We go through all the directions, all the 4 directions. We add the X by the direction 0 and Y by direction 1. That's going to give you a new X and new Y. And the new X, new Y is going to be 1 hop away from X and Y. It's going to be either on the left side of it, or on the right side of it, or on the top of it, or on the bottom of it. So it's going to be one of the 4 neighboring squares. If new X and new Y are within the same square shape field of simulation, we are going to add them to the list of all neighbors. If not, then we don't add them. How do we know if they are inbound or out of bound? New X and new Y should both be non-negative. They cannot be negative. And they cannot exceed the size. So that means they should not pass the boundaries of the square shape field. If that's not the case, then we're gonna add them to the new to the neighbor list, which was an array list of interarrays, and at the end we're gonna return those neighbors. This is gonna become either an array list of 4 squares at most, if your square X and Y is not on the boundaries of your square shape field. But if it's on the boundaries, then the neighbors would be made of 3 interarrays, because you have 3 squares, or it's going to be only 2 if the X and Y are on the corners. For example, if you pass X equal to 0 and Y equal to 0, then the neighbors would be only 0, 1 and 1, 0. So let me give you an example. If X and Y are equal to 0 and 0, the neighbors would give you a list of 0, 1 and 1, 0. Or if the X and Y is going to be 1 and 1, let's make it a little complicated, 1 and 2, then the output would look like this. 1 and 1, 1 and 3, 0 and 2, 2 and 2. These four are going to be the four neighbors of this cell. And if it's 0, 0, you only have like two neighbors because this is like in the corner, and not all four neighbors are going to be inbound. Two of them are going to be out of bound. So that's the explanation of the praise move method. You need to find the neighboring squares first. If the neighbors are empty, which is impossible, so you don't really need to have this if statement. I only have it here because later, if you want to extend this simulation to add the obstacles on the field and say some of the squares are obstacles, like they are mountains that you cannot pass, or these are like lakes that the animals cannot walk on them, then you just the neighbor's set can become empty if an animal is surrounded by obstacles on the field. But that's not a big deal, just ignore it. If it's not empty, then create a random number. That random number would be a number from 0 all the way to the size of neighbors minus 1. So if you have 4 neighbors, it would be 3, from 0 to 3, either 0, 1, 2, or 3. And this random number basically choose one of the neighbors randomly. Remember, the neighbors were in this list. This is going to choose one of the 4 neighbors, or if you have like 2 neighbors, one of the 2 neighbors randomly, and then gets their location. That new location should be passed to the Board.updatePosition to update the position of the prey to this location. And at the end, you're going to return true. Return false will not happen in this thing, but as I said, if you have some obstacles on the board, then it may happen. Let's look at the mouse as well. Mouse is the only class here that extends prey. And then the symbol is M, the toString method returns the ID, the location, X and Y. Now let me run it first before I show you what you need to do. I'm going to run this. Let me run it once. So the minimum values you can pass is 6 for N and 2 for K. As you see, the simulation lasted about 3 seconds. Initially, you had 2 mice, because K is 2, you have 2 mice. You have 2 alligators and 2 cats. As you can guess, this alligator is so close to the mouse that in the next iteration, the alligator at index 0 and 4, which is this one, is going to eat the mouse at index 0, 5. So as I told you, the Y value shows which column you are. So it's, the greater the Y is, the further you are into the right. So this alligator is going to eat the mouse. So now the next iteration, alligator is going to be here. The mouse is not going to be anywhere else in the map. So the mouse is deleted from the map because it's eaten by the alligator. The other mouse has moved forward. You see the mouse was here. Now it moves, I'm sorry, it moves upward toward the alligator that has already eaten one of the 2 mice. And then the other predators, like the cat, the alligator, the other cat, they're all moving toward the mouse. So if you remember, it was the cat was here. Now it's on the upper row. You see this cat has moved up So in the next iteration, now it's on the row number 0, 1, 2, 3, 4. And it's getting closer to this mouse to eat the mouse. The alligator also closer to the mouse than before. It was on this column, now it's on this column. The cat on the left side of the board tried to get closer to the mouse, but unfortunately, after the cat comes down to catch the mouse went up. So it didn't get closer to the mouse because the mouse moved. In the next iteration, the alligator that ate the first mouse now is gonna come down to catch the other mouse. This mouse has moved to the left, and the cat and the alligator have moved up to eat the mouse. So these two are the closest to the prey, and then the other cat is now very close to the prey. In the next iteration, the cat at index 3, 3, which is this one, ate the mouse at index 3, 4, which is this one. So this cat ate this mouse. The cat is now here. The alligator that was following the cat is now here. The other alligator is here. So they're all very close to the location of the mouse that was eaten. The other cat is also moving to the right to eat the mouse, but unfortunately, this cat was first to eat the mouse. So the two mice were eaten by one alligator and one cat. And the other alligator and the other cat starved to death. End of simulation, and that's it. If I run this one more time, I see a totally different scenario. Let me put same numbers, 2 and 6 and 2. Now my simulation took a much longer time. It took 8 seconds. And if you go through that, you see, we had like two mice here and here. The first mouse is eaten by a cat, which is this one. And then I'm sorry. Yeah, I was right. And the alligator ate the cat. So first the cat ate the mouse, then the alligator ate the cat. So you see like a different scenario. You can go through that, and at the very, very end, all the mice are dead, and all the alligators and cats are either all of them are here, or in this case, at the end, you had only one cat and two alligators because one of the cats were eaten by an alligator. So it can happen, but the only unlikely scenario, the only thing that won't happen is that no alligator eats another alligator. So alligators will still be alive at the end because they have the highest power between the existing predators. And every time you run it, you get a different result. But if you want to keep the same exact result every time, go to the animal simulation.Java and go to line 21 and replace random constructor with random 0. Give it a seed 0, and now when you run it, no matter how many times you run it, it's going to always give you the same answer, the same output for a given n and k. So if n is 6, k is 2, you always get this situation where we start with 2 cats, 2 mouse, 2 alligators, and we have a lot of eating events, and as you see, at the end, you only have 2 alligators because all the cats and mice have been eaten by alligators. And then at the end, you only have like 2 alligators, and the final time is 5. But on this again, now that I have set the C to 0, I'm sorry, n should be 6, not 5. The minimum is 6. So if I put 6 and then 2, it's going to take again 5 seconds, and we're going to end up with the same exact output. Let me try it one last time. And 6, K2, same exact output. So when the seed is 0, always you're going to get the same result. And the maximum values you can pass would be n equal to 25 and k equal to 5. That's going to give you a giant output. And as you see, 19 seconds passed until all the mice are eaten by our 5 alligators. You see we have 5 alligators. And then we have 1, 2, 3, 4 cats left. One of the cats were eaten by one of the alligators. You can check the output here. So it took like 19 different steps until all of them were eaten. So it's pretty complicated if you want to increase the values of n and k. But try it with 6 and 2. 6 and 2 are great. And then leave the seed to 0 so that, you know, you have a deterministic output. Try it for multiple times if you have errors to fix it. Debugging with a random, with no seed is pretty complicated. So always give a seed, like 0 in this case, to your random number generator so that you can test your simulation and make sure the simulation works in a certain non-deterministic, non-randomized manner. Last thing I want to mention is what you need to do. What you need to do is pretty simple. You need to add more animals, preys and predators. I have explained all the details that you need to know, but basically you don't need to update most part of this code. The only parts that you need to update is you need to go to the package animals and add more animals. The details are in the on canvas, and then you need to update the initialize board method. Right now I have only added K cats, K alligators, and K mice. You need to add K instances of the new animals that you're going to add to this simulation, and then you need to run it, and then you need to, you know, print the output and put it in your report so we can see you have done it successfully. That's pretty much it. Thank you.